Okay, diffusion process. Hmm. Let me bring the drawer pencil here. Okay, so let's see what is a diffusion process. Diffusion process is basically used for making or creating the impurity regions inside the substrate or inside the semiconductor material. So look at here. This is a p-type substrate, okay, and on the top of it we have a layer of SiO2, and this window is open, okay, and this is again SiO2 layer. Sorry. And after performing the diffusion process or bombarding it with the impurity ions, okay, what happens that since this region is available, okay, so the ions that are coming and interacting to this surface which is open, okay, they will enter up to a certain depth, inside the p substrate area, okay, and they will form uh, n well, because this is pentavalent impurity, okay, and this will form one n well or n type of region in this p-type substrate, okay. So look at the difference here, that we wanted to create one n well in a p-type substrate. So with the help of diffusion process we achieved this, right? So basically this diffusion process are being used for creating these kind of regions. So we sometimes we want to create n well regions, sometime we will want to have p well regions, okay. So whatever region we want inside the substrate, okay, this is not getting deposited, this is created inside the substrate area, right? So there is a difference between, deposition and diffusion, okay. So with this thing in mind, basically the diffusion process is having this definition that the atoms move from a high concentration region to a low concentration region. This is the basic definition. We know that, we know this, right? But in VLSI fabrication, this is a method to introduce impurity atoms or dopants, okay, into silicon to change its resistivity, right? So the resistivity of this area will be different from the resistivity of this area, and whose resistivity will be low? This area resistivity will be low because this contains impurity atoms, okay, and hence it will be more conducting in nature as compared to this particular area, right? Okay, so diffusion of impurities is usually carried out at high temperatures. So this is being done at around 1000 to 1200 degrees Celsius to obtain the desired doping profile, okay. So the diffusion process is performed in furnaces similar to those used for oxidation. So these are performed inside furnaces because the temperature requirement is very high. So it is performed usually inside furnace that can handle this kind of temperature. The depth to which the impurities diffuse depends on both the temperature and the processing time. Okay, so this is the depth that this we have in this figure, the depth of this n well, okay. Now this depth of what depth we want to achieve, or we want to diffuse the ions in this in the wafer, okay. So this depth can be controlled by and this is a function of two parameters, what, the temperature and the processing time, okay. So if you perform diffusion for a longer duration of time, then in that case the depth achieved will be more, and if you perform diffusion for a less duration of time, then in that case the depth will be less, okay. And the most common impurities used as dopants are boron, phosphorus and arsenic, okay. These are the same dopants that are used for creating or making p-type or n-type semiconductors, right? So those same impurities are also used here for creating n-well or p-well regions, right? Okay, so this is the basic about diffusion. Then there is one more thing, one more term known as ion implantation. Okay, so what is this basically? Ion implantation is another method used to introduce impurities into the semiconductor crystal. Okay, introduce impurities again. This is a process again used for introducing impurities in a semiconductor material, right? So an ion implanter produces ions of desired dopant, accelerates them by an electric field, and allows them to strike the semiconductor surface. Okay, the the ions become embedded in the crystal lattice. So what is done here is the surface of the um, this uh, substrate area, okay, where we want to have and where we want to create uh, an N well or P well, okay, that particular surface is bombarded with high energy ions, with high energy impurity ions, okay, and these high energy impurities ions, when they uh, come in contact with the surface of the substrate, they get inserted or they get embedded into the body of the substrate, okay, and then that creates the desired N well or P well. So this is similar, this looks similar to here like this. So I can explain this ion implantation method by using this same diagram, okay. So the thing is that here we are having in the case of ion implantation method, these are high energy, this is difficult to write, these are high energy, okay, these are high energy particles, these are high energy ions. Which type of ions? These are basically these are high energy uh, impurity ions, whatever impurity ions you want to use, whether pentavalent impurity ions or trivalent impurity ions, okay. So since these are very high energy ions, and when they come and when they are bombarded on the surface of this, okay, they get penetrated inside the substrate area, right, and this penetration depth will be directly proportional to the energy of these ions. Definitely higher is the amount of energy, more will be the depth of penetration, and more will be the depth of N well that is to be formed, right. Okay, so okay, here, so the depth of penetration is related to the energy of the ion beam, okay, which can be controlled by the accelerating field voltage. So the energy content of the ion beam will be directly proportional to the depth of the diffusion area that we want to create, okay, and the energy of these ion beam can be controlled by the applied voltage, okay, applied accelerating voltage. So, and since this is some voltage, external voltage, external electric field is required to accelerate the ions to a very high value of energy. So in this case the amount of voltage required will be high, okay, the input electric field required will be high, right. The quantity of ions implanted can be controlled by varying the beam current flow, okay. Since both voltage and current can be accurately measured and controlled, ion implantation results in impurity profiles that are much more accurate and reproducible than what can be obtained by diffusion. So this process gives us a more controlled, a more accurate and reproducible uh, impurity profiles within the substrate area, okay. So this seems to be a bit more beneficial than uh, than the previous method, that is the diffusion method, right. But what is the difference here? Here we required high temperature, and here we require high input voltage. Okay. So the advantage of this ion implantation is that this process can be performed at room temperature. This process can be performed at room temperature, but this will require a high amount of voltage, so that the impurity ions can be accelerated to a high value of kinetic energy. Okay, right. So the next method is chemical vapor deposition. Okay. So look at this term deposition, right? So this is a method that will be used for depositing extra layer over the surface of substrate. Okay, this will not be emmed, or this will not uh, be fabricated, like this will not get inserted within the substrate area. This will be deposited over the substrate area, and hence this will increase the thickness, the overall thickness of the substrate. Okay, so there is a difference between deposition and that region that was created within the substrate. Okay, so this gets added to the above the surface of substrate area, right? So this chemical vapor deposition is a process by which gases or vapors are chemically reacted, leading to the formation of solids on a substrate. Okay, so this use the chemical reactions between the materials to form the layers, the layers of solid, or the layers of materials on the top of the substrate. Okay, so this CVD can be used to deposit various materials on a silicon substrate, including SiO2, Si3 and 4, this is silicon dioxide, silicon nitride, polysilicon, and so on. Okay, so for instance, if silane gas and oxygen are allowed to react above a silicon substrate, okay, the end product, that is silicon dioxide, will be deposited as a solid film on the silicon water surface, silicon wafer surface. So if we want to deposit a layer of silicon dioxide, okay, then one method could be to have a reaction between silane gas and oxygen, in a closed chamber, so that the product of this reaction will get deposited on the top of the wafer surface. Okay, the properties of the CVD oxide layer are not as good as those of thermally grown oxide, but they are sufficient to allow the layer to act as an electrical insulator. So the quality that we get in this process is not as good as we obtain in the case of thermal oxidation. This is not as good. Okay, but this is just sufficient to fabricate an insulating layer. If the quality does not matter in certain cases, if we don't worry about the quality, if we just want to fabricate a layer of insulator, then we can use in those situations this particular method, that is chemical vapor deposition. Okay, the advantages of a CVD layer is that the oxide deposits at a faster rate, and at a lower temperature, that is below 500 degrees Celsius. But in the case of those thermal oxidations, we required temperatures above 1000 degrees Celsius. Okay, so this is advantageous in these terms. Okay, but the quality will not be as good as the layer that we obtain in the case of thermal oxidation. Okay, so this tells about the polycrystalline silicon. This is material that is widely used in the fabrication of VLSI chips. Okay, so polysilicon, why it is called polycrystalline silicon? Because it consists of many small crystals of silicon aligned in random fashion. Okay, this is not a single crystal material. Inside it there will be many small crystals aligned in random fashion. Okay, and polysilicon layers are normally doped very heavily to form highly conductive regions that can be used for electrical interconnections. So normally without doping, the polycrystalline silicon will be having a higher resistivity. Okay, but the resistivity can be reduced or the conductivity can be increased by doping the polycrystalline silicon. Okay, so this polycrystalline or silicon or polysilicon or simply uh, polysilicon or polymaterial is used for the forming interconnections between different gates of transistors. Like if you remember, I had told you some classes some time back that there was one polysilicon layer between the gate of nMOS and PMOS. Hmm. So this is basically used for connecting different parts of the components polysilicon. Okay, I think this is the last term. Yeah, this is the last one. So we have another common method uh, called as metallization. So after when we fabricate the IC, okay, that is when we fabricate the components on the surface of IC, we would need to connect those components in a certain fashion so as to create a particular circuit and hence to realize a particular function. Okay, because without connecting those components, it will not be of any use. They will be still unused or uncommitted transistors. So metallization is the process help that will help us in connecting or interconnecting the different components or different transistors that we have fabricated on an IC. Okay, so the purpose of metallization is to interconnect the various components, transistors, capacitors, etc. to form the desired integrated circuit. So the purpose is to interconnect the various components. Fine. Okay. The metallization involves the deposition of a metal over the entire surface of the silicon. So how is this interconnection achieved? This is achieved by the deposition of metal layer over the entire surface of the silicon. Okay, now the entire surface of the silicon is covered with metal, and the area wherever we require this metal layer to be present, and there are certain area where we don't require these metals to be present. Okay, so from those areas where we don't require metal lines to be present, from those areas the metal layer is simply etched out. Okay, we call this as patterning that we have seen already. Okay, so the required interconnection pattern with the help of mask again, right? If you remember the mask, that's a very important component in VLSI fabrication. The required interconnection pattern is then selectively etched. Okay, the metal layer is normally deposited via a sputtering process. The deposition of metal layer is achieved with the help of a process known as sputtering. Okay, so in what happens here, look at in this diagram that shows the uh, process of sputtering. uh, so this is the metal that is to be deposited on the top of substrate, and this is the substrate or the wafer. Okay, so I want to deposit this metal on the surface of this substrate, that is along you know this area, let's say. Okay, so this is a chamber in which high vacuum is maintained, and this is bombarded with high energy sputtering gas, that is usually an inert gas. Okay, inert ions, for example argon plus, so that they does not react with the metal and other IC material, IC area. Okay, so it is bombarded with the high energy and inert ions, and when they come and hit this metal, okay, the metal ions are produced from this. As a result of this impact, the metal ions are produced, which then go and gets deposited over the surface of this particular substrate area. Okay, so this is how this particular sputtering process is done, right? A pure metal disc is placed under an argon ion gun inside a vacuum chamber. Okay, so this is the vacuum chamber. Okay. The ions are made to physically bombard the target and literally knock metal atoms out of the target. This is uh, the target of argon ions. Okay, the argon ions are uh, uh, bombarded inside this vacuum chamber by keeping this particular metal as the target substance. Okay, these metal atoms will then coat all the surface inside the chamber, including the wafers. So because these are produced in every direction, so even uh, the inside of the chamber also gets filled, also gets covered with the metal atom, including the top of the substrate area where we actually want to deposit the metal atoms. Okay, the thickness of the metal film can be controlled by the length of the sputtering time, which is normally in the range of 1 to 2 minutes. Okay, so we can also uh, control the thickness of the layer that is deposited, and this thickness will be controlled by the length of the time for which this sputtering process is done. Okay, and usually this is typically in the range of 1 to 2 minutes. Okay, okay, chalo. So after looking at these uh, uh, common methods that will be used in IC fabrication, so what methods we have seen till now? Just a quick recap. So metallization for forming metals like aluminium, copper, etc. Okay. Then chemical vapor deposition uh, is used for depositing a layer on the top of silicon substrate. Okay, like depositing silicon sorry, like depositing silicon dioxide layer and others. Ion implantation, what is this? This is used for creating impurity regions within the substrate area. Okay, not on the top, within the substrate area. And diffusion is also a method to create the impurity region inside the substrate area. Okay, then we saw etching, when we want to etch out some layer. Then the issues in etching, undercut issues. This is anisotropic etching, where undercut does not appear, undercut issues are overcome. Then we saw photolithography. Okay, photolithography was used for patterning different layers, right? For example, I want to form this kind of geometry over this silicon substrate from this, then photolithography process can be used. Okay, and in the very beginning we saw oxidation. Oxidation was used for forming oxide layer on the top of silicon substrate. Okay, so this is a silicon substrate before oxidation, and this is after oxidation. A silicon dioxide layer is formed on the top of silicon substrate. Okay, and it start with the crystal growth, that is in the form of a single a silicon cylinder, and this is cut in the form of slices that are actually called silicon wafers. Okay, so oxidation, photolithography, then etching, then diffusion, ion implantation, then chemical vapor deposition, metallization. These are the common methods that are actually used repeatedly in IC fabrication. So now coming on to the fabrication process steps. Okay, so let's start with the uh, basic steps in a fabrication process that are used. Okay, so we start with the silicon substrate. Okay, and then we deposit one SiO2 layer over this with the help of which technique can be used. Oxidation can be used here to deposit, this SiO2 layer on the top of silicon substrate. Okay, right. Then one photoresist layer is deposited on the top of this oxide layer, right? Then this is a glass mask with features. So this is a glass mask having some opaque area and some transparent area. That is the actual geometry of the of the shape that we want to transfer on the top of this silicon substrate. Okay, so we want to get this one. We want to get this kind of patterning in the final stage. So this is one layer, this is open, this is blocked window. So this is the open window, and hence the shape of the geometry on on this mask is like this. This is opaque, this is open, this is again opaque. Okay, opaque, open, and opaque, right? Okay, now when glass masks are placed on the top of this silicon substrate. Okay, so by using this mask and by using ultraviolet rays bombardment, we define the area uh, which is to be achieved at the end of this fabrication process. Okay, so this UV rays, when they are bombarded, they come and touch this photoresist material. Okay, and depending on the type of the photoresist material, it will either become soft or hard, right? So let's say this exposed area to UV rays of the photoresist is becoming soft actually. Okay, and they are etched out with some chemical solvent. Okay, and the areas which did not get exposed to ultraviolet rays, they remained hard. So what type of photoresist material is this? Can you guess? Is it positive photoresist or negative photoresist material? Just think about it. Hmm. Okay, so I think you might have thought about it. You might have got the answer, right? So uh, now after getting this structure, okay, we perform the the etching process. Sorry. So with the help of some other solvents, this particular layer of SiO2 is also, etched out. Okay, so we get this particular open window. This window is open. Why open? Because from this in this through this window, the surface of silicon is visible, right? Okay, and in the last step, this hardened photoresist material is also etched out with the help of some other solvents. Okay, and we are left with this only silicon substrate, and over the top of it we have a layer of silicon dioxide, such that only one window is open on the top of silicon substrate area. Okay, so the starting from this initial, the target was this: to form one simple window that is open. How many steps are required? 1, 2, 3, 4, 5, 6. Okay, so at least 6, and these are minded, these are major steps, not in detail. In details there would be several steps, maybe some in tens of, or some 50s of hundreds of steps. Okay, in actual practice, in actual fabrication, but here only major steps are shown. Okay, so what did we achieve in this slide? We achieved from this to this this is the front view, only front view. We are not showing it from the top. Okay, but how would it look like from the top? This is the three-dimensional view. Okay, So this particular substrate has got certain length. This is the length, okay, and this is the width of this substrate area. Okay, so I think this will be more clear. Okay, this will be giving more clear concepts. So this is not a just a two-dimensional thing. This is actually a three-dimensional material. Okay, so after patterning, if you look from the top, it will look like this. Okay. Okay, now by looking at this basic uh, step that is used for forming a single open window here. Okay, now we can go for the fabrication of nMOS transistor. Right.